Here's another question from the fluid mechanics exam that I sat as a first year undergraduate aerospace engineering student in the academic year 2010-2011. Okay, so this question was a part of question 5 from that paper. So there were 6 questions in total. And actually, the first part of question 5, we're not going to go over it now because it's just a bit of theory. There is a question which is asking you to state the principle of momentum conservation. Okay. So again, that's something that you can probably find in any fluid mechanics textbook. And we're going to apply that in the second part of this question. So this is what we're looking at. We're dealing with a pipe, or how the question calls it, a horizontal duct of side H. And the important thing to note is that the cross section is square. So we're no longer dealing with, when you find the area of the pipe, this is no longer pi r squared. Okay, this is, in this case, you've got the area as just h squared, right? It's the area of the square. And at first, we're dealing with a water flow. So at the inlet, we have water flow with a velocity u, or I guess more correct, it should be u1, just to be, just to respect the diagram as well. Okay, this has a final piece attached loosely to it, which itself has a takeoff pipe attached to one side of the duct. So basically what happens is you've got a duct, and then at some point on that duct, there is another duct which is attached, and that goes, in this case, downwards. Okay, so some of that fluid from here will start going through that takeoff pipe, and the remaining fluid will keep going through the main pipe like this. Okay, and what we know is a mass flux of 1/10 of the inlet mass flux is removed from the duct via the takeoff pipe. So if this mass flux here is m dot, right, the mass flux going through the takeoff pipe is 1/10 m dot, which means that, because conservation of mass is a thing, then the amount of mass flow rate through this is going to be 9/10 m dot. So the sum of those two has to be the same as the inlet mass flow rate. And what we're asked to find, first of all, is find the velocity u2 at the duct exit and the pressure difference P2 minus P1 across the exit piece in terms of the inlet velocity. So it's a relatively straightforward question, I would say. So the first thing I would do is I would use the fact that the mass flow rate is obviously conserved. Okay, so let's see how we can actually do that. So I'll say that the mass flow rate m dot is going to be equal to rho times the area and then times u1. And this is the same as, so the same mass flow rate m dot can be written as the sum of the mass flow rate through the takeoff pipe, which is rho. This is an unknown area. Let's call it AT for the takeoff area. And then this velocity here is, again, unknown, plus rho. And then we have A times U2. Okay, so let's talk about this for a second. So first of all, the inlet mass flow rate is just given by the density, the area, and the velocity. Okay, and the mass flow rate coming out, which has to be equal to this as well because of continuity. First of all, the mass flow rate through the takeoff pipe is given by density, area of the takeoff pipe, or area of the cross section of the takeoff pipe, times the velocity of the fluid going through that takeoff pipe, plus, and this is the mass flow rate going through the remaining pipe. Okay, so let's see how we can actually use this, because at this point, if you think about it, we don't know anything about this term. But what we do know is that this term is 1/10 of m dot, or 1/10 of rho a u1. So we're going to replace the whole thing with this. And this is what we'll get. We have m dot equals 1 over 10, so instead of this stuff that I put in a yellow rectangle, I'm gonna write 1 over 10 rho A1 U1, and or just rho A U1, I think. That's probably better. And this m dot at the beginning, let's just replace this with rho AU1 as well. Right? Just as a reminder, this is m dot plus, and then we have this. This is the mass flow going through the right-hand side of the pipe. So that's going to be rho, that's going to be A, and that's going to be U2. Okay, so now it's pretty straightforward to find what U2 is, because there are some things that simplify quite nicely. So we have rho A cancels out from everywhere, so we just end up with U1 is equal to U1 over 10 plus U2, which means that U2 is, well, 9 over 10 U1. Okay, so that's what U2 is. And we found the velocity therefore here. So you might be used to the idea that if the diameter of the pipe is constant, the velocity shouldn't change, right? And what happens in our case? Well, it does change. So if the diameter of the pipe stays the same, the velocity should be constant, but in our problem, the velocity here, the U2, is less than U1. But keep in mind that happens because some of that flow rate is actually discharged through this extra pipe that we have here. So the mass flow rate here is less than the mass flow rate at the inlet, which in turn produces a lower velocity. Okay, so that's the difference. So now that we found this, or now that we found U2 in terms of U1, let's actually think about how we can find some relationship between the pressure at 1 and the pressure at 2. And again, this is quite easy to do, because if you consider a streamline that passes from point 1 to point 2, and when I say streamline in the context of first year fluid mechanics, you should think about Bernoulli. So this is exactly what we're going to use. So let's say that we apply Bernoulli at point 1, so that's static pressure at 1 plus half rho U1 squared. There's no potential energy term because the streamline is just horizontal all the way through. So that is equal to P2 plus 1 half rho, and then we have U2 squared like this. So I think the question was asking for P2 minus P1. Yeah. So let's take the P1 and let's move it to the other side. And then let's take this and let's put it here. So what we end up with is 1 half rho U1 squared minus 1 half rho U2 squared. That's equal to P2 minus P1. So let's move this somewhere else. So this is P2 minus P1 essentially. So we've written P2 minus P1 in terms of the velocities, but we actually have to write P2 minus P1 in terms of just U1 and not U2. But we know, or we found from earlier, that U2 is 9 over 10 U1. So we're going to take this, we're going to put it here. So we end up with this delta P, the change in pressure, is 1 half rho, and then we have U1 squared minus, so it's 9 over 10 U1, everything squared. So that's going to be 81 over 100 U1 squared, which is 1 over 10 rho. We can take the U1 squared out, and this is going to be 1 minus 81 over 100, which is 1 half rho U1 squared. Okay, so 100 minus 81, that should be 19 over 100. So the delta P, or P2 minus P1, is going to be 19 over 200 rho U1 squared. So there you go. It's just the pressure, or the change in pressure, simply in terms of the inlet velocity and of course the water, the density of the liquid. And that's it. And you can see that in this case, the pressure is increasing. Okay, so this is the Bernoulli equation that we started from. And then when we move things around, when we try to find this P2 minus P1, we end up with a higher pressure at point 2 than at 1. Okay? And that can be explained, of course, by the fact that the velocity decreases. So the velocity decreases, which means the pressure increases, which means that this pressure difference is positive, which means that, of course, P2 is bigger than P1, which is what we would have expected. Okay, and those are some, I think, relatively easy to get 9 marks for this particular question. And that's the end of it.